All right, it's 1:01. I think we'll get started. Thank you everyone for joining us. For guests joining now, all our microphones are muted until the end, when we'll be able to open up all the mics and have a discussion about any questions you might have. If you have any questions during the presentation, just put them in the chat so we can see them, and if we need to, we can pause and address the questions at that time. So today we're going to talk about STAR-CCM Plus and CFD coupled with the discrete element modeling for particles. I'm Adam Green from ATA Engineering, and joining us from Siemens is Dr. Ravi Aglave. I'll ask him to introduce himself when he comes to his presentation. So just a few notes. Let's get started and talk a little bit about really who are ATA and why are we kind of involved in this with Siemens. And so really who are ATA Engineering? We're an employee-owned small business engineering consulting company, and we have around 180 people, 30 which are PhDs, 80 are masters, and over 27 are just bachelors, and really a very highly skilled group of people in an employee-owned company as a consulting engineering team. And what kind of work do? We work in various sectors, and we really do kind of very high-end engineering services, really the hard problems that not many people want to tackle, we tend to do. We work in the aerospace and defense sectors primarily, but we also do robotics and controls, and some themed entertainment and industrial and mining equipment, as well as some consumer products. So that's really where the relevance here today with DEM. And so when we look at our services, what we actually do, we focus on analysis and design, and really test-driven design especially. And we really pride ourselves in being able to do basically ground vehicle testing of large aircraft, all the way down to designing and analyzing basically amusement park rides. So we tackle the whole gambit, but again, the hard problems. And so we do full design, we do full analysis, and we do full test. And you can see the locations on the map where we have offices, mostly in the aerospace centers of those parts of the US. But then at the core of all of that is also our partnership with Siemens. We are the Siemens Platinum level reseller, which basically means that we sell and support many of the SimCenter tools from Siemens. And we support them with a very skilled group of individuals, all of which are using those tools in consulting services all the time. So the skill level is very high, and responses to support is really very, very quick and at a very high level. And so that's ATA, the quick introduction, and really the CFD and the DEM part of STAR I'm going to leave to Ravi to talk about. But I wanted to show a video really just to kick off everyone's thoughts about DEM and CFD and the combined technology that brings. So let's just watch this. It's about a minute, so we hopefully will be good with that. And so, at the basic level, a DEM solver could model this on its own without any fluids, just modeling the dynamics of the particles, moving things around. With STAR, you can actually change the CAD and the shape of particles. This is highlighting some obscure shapes being moved around. And then coupling it with 3D moving geometry and solids to actually do this kind of conveying, is also a part of STAR-CCM Plus. Now all of those you've just seen could really have been modeled without any fluids. But many problems really need both the DEM pass to model the particles coupled with the fluid solver, such as, in the oil industry, moving oil and water with a slurry of sand inside, or particles through a valve like this example, where basically the particles become an integral part of the flow, and both impact each other. So, and finally, really the last piece is also the chemistry and the physics of particles. This is actually a melting bed of particles. I'm not sure what they are, but they're melting into a fluid, and STAR can cope with really all of the phases there, and the phase and mass transfer as things melt. So you can imagine the applications to this particular example, this last one. And so that kind of hopefully will have got people thinking more questions than really any answers so far. But really suffice to say, STAR-CCM Plus has DEM built in. it's part of a standard license. So anyone on the call, and I know there's a few who already have STAR-CCM Plus, are able to use this now, today if they wanted to. So there's no extra licensing, it's built in and ready to go. So with that, I am going to pass the ball to Ravi. Ravi, are you ready?
Yes, thank you, Adam. So thank you, Adam, for inviting me to speak here today in this webinar. I was just talking to you, Adam. I have a fifth grader girl, and she likes to make these bracelets with all these colorful threads, and she's really gotten skilled at making different patterns on them, heart shaped and flowers and things like that. And before I knew how she was doing that, when I looked at it, it looked to me pretty complicated, because it was, taking out many of these different colored threads and putting them into a certain weave to create that. And so I asked him that, how does she do it? So she said that you just need to understand how each thread is weaving into the other, and you have to follow, certain rules in achieving those patterns, and then boom, you have sort of the design that you need. And if we look at the problems in physics, they are somewhat similar. That there is complexity of various physics that is involved, in the sense that you have fluid flow, you have particle flow, sometimes heat transfer, and all the other physics that is involved. And when we try to solve such industrial problems, we have sort of a few choices. One is do nothing, completely ignore them, and then deal with the consequences. Most often what we do is we simplify them. We say that I'm going to look at only one part of the physics, and then we go and say, oh, now I'm going to look at other part of the physics, and then we try to make sense of how these two could be interacting with each other. When we look at engineering problems and the solutions that we try to create, it was with the idea or a concept that if we can resolve this complexity, we can understand it better. And if we understand it better, then we can solve those problems with their complexities, and therefore achieve higher values, of course, impacting business as well. And that is what you already explained, Adam, to some degree. How can we improve and understand such complex operations by coupling various parts of the physics? I do want to mention here that when we speak about coupling, there are quite a few different notions, in the sense that you can have one way of solving one part of the physics, another way of solving other part of the physics, and then you can look at the results and make sense of it. And that would be the lowest level of things that one can achieve. The second would be that you take data from the first and send it to the next, and then take data back from the second and send it to the first. And that is what you can call maybe co-simulation, that there are two different physics running independently. And then there is the coupling approach, where these two things sort of sit in the same platform, share maybe the same solver spaces and variables and so forth. And that is kind of is the focus of what I want to speak about. But when we want to talk about these problems that involve flow of fluids and flow of particles, there are certain key requirements that one needs to satisfy, that it can address a wide range of materials. And I'm going to speak about how we do that. That it addresses various boundary types and the motions that are involved in the dynamic bodies. And Adam, I think you showed some good examples of that. But the most important one here is how the particle flow solver and the fluid flow solver can be coupled, and that there is a interaction between these two phases in order to capture all the nuances of the physics. Of course, there are a lot of other things. So there are multi-phase interactions, as in if there are more than one fluid phases, how will they interact with each other? There are requirements in terms of that we can scale these things very well on high performance computing platforms. And eventually, after the simulation is over, we can analyze the data in a meaningful way. And I'm going to speak just a bit about how it is not a single simulation, but multiple simulations that are necessary to achieve that goal. So when we are able to satisfy these requirements, here you see an example of a bag being filled by particles, and that causes displacement on the body of the bag. You can see the displacement magnitudes that is shown here. Adam showed this example where there is a erosive effect on the wall of a pipeline. But at the same time, when there is an erosion, that we can morph the wall in order to account for the changing shape of the pipeline. That is the type of complexity of physics that I'm talking about, that we can include in our simulations. So the STAR-CCM Plus platform, if you know it or if you don't know it, is worth mentioning, is that it has a CFD solver, which is a finite volume-based solver. There is also a finite element flow solver that is primarily for viscous and viscoelastic fluids. There is the discrete element particle flow solver, which is coupled with the finite volume flow solver. And then there is a finite element thermal and stress solver, which is also coupled with the flow solver, especially for problems that are tightly coupled in that sense. So it's a multiple solvers in a single environment. And what it allows us to do is really to investigate effects that are otherwise quite difficult to figure out. So if you have sand particles that are melting due to heat that is applied to them, and then eventually being converted into a flowing glass at the bottom here. And this is just a square box example establishing the feasibility of being able to do that. So having looked at from a generic point of view what these capabilities capture the range of physics, we can look at some few examples of this. But the key thing is we have to understand we can define fluids using either a Newton's law or some sort of a non-Newtonian constitutive equation. That means a small droplet of fluid will have similar behavior that a large body of fluid will have from a rheological perspective. And that is not true when it comes to particles, right? So if we want to investigate many of these different industrial applications, which includes pneumatic conveying, fluidization, calciners, segregation, coating, drying, and so forth, we need to understand that how does a single particle behave, but at the same time, then how do a bulk of particles behave? And to achieve that, then one needs to look at how can I characterize my material? So most of these simulations will need to start with a material characterization exercise. This is something that is unique because when you do CFD simulations, you have the viscosity or a viscosity temperature relationship, perhaps from literature, and then you're ready to go. However, this is not true for particle fluids. There are many different physical events that are involved in defining how the bulk particles will behave. That means that if you have same material, let's say stone, and particles of a certain size, say 1 millimeter, versus stone, which are particles of a different shape and a different size, their bulk behavior could be different compared to the small particles. So we can do this exercise of modeling the real world behavior of the granular systems by doing a calibration exercise to arrive at a model that gives me all these required quantities in the model. And once I have done that, then I'm ready to go along with performing the rest of the simulation. So it generally can start with some sort of a characterization experiment, which includes effects like density, particle size, which then gives me the friction parameters, the Young's modulus, as well as any other rheological behavior. We did a lot of this investigation as part of a master's thesis, which was published a couple of years back from Purdue University. If you need this reference, feel free to ping me and I can send you this. This is giving you that example that using a shear cell test, you can look at, for example, the coefficient of sliding friction versus rolling friction. And there are several different tests that were involved. So angle of repose test, a shear cell test, and a multi-objective optimization, which means that varying these coefficients until we get the right set of combinations that is reflecting what is happening in reality. So for example, what is the angle of repose or what sort of shear that I would get from this test. So that is kind of the basic step that is required in order to characterize the material. Here you can see what sort of equipment were used in carrying those tests out. And once we have this information, then we can start looking at some real scale problems. So this is coming from a steel company where the hopper discharge rate was a problem that needed to be resolved. The key question was how to determine flow characteristics and the regime of particle flows in this bin hopper assembly with a certain particle size distribution. You can look at these images showing you that distribution. So there is a cylindrical bucket that is unloading, and the angle of repose tests were used to do this calibration. And we then automated the whole process of movement of this bucket, the start of the discharge from the bin onto the lower hopper, and investigated what is the mass that is left on the top hopper, which is an effect of the shape and the friction characteristics of this. So what is to be avoided is that there is some material that is still left at the end of this process. And when we included the particle size distribution at the exit, it showed that there was a segregation effect. That means small particles versus large particles, they move at different rates, which can then cause a certain amount of particles of certain size being left in the upper part of the hopper. Sort of similar type of investigation was done. This was for formation of a sand mold process, again in the steel and casting industry. So you have a chamber here, which is filled with sand to create the mold. And this cavity had a special design, which had some air vents to let the air out. And the air vents, they transport the green sand with an airflow during this sand shot. So with correct material characterization, it's possible to simulate the experimental video footage. There is very little that can be done in terms of measuring the process, but a visual comparison can be done very well. So here we look at the drop of the sand particles at various time shots, and then it is compared to the closest one that was available from the camera that sat inside the cavity. And so the geometrical configuration as well as the applied compressed air pressure is the factors that affect this filling pattern of the mold. And by changing the air vent settings in the chamber and in the cavities, it was possible to improve this filling process also in sort of the narrow passages that were part of the cavity design. So therefore, improving the final sand mold as well. And this design was critical in the final casting product that was to be developed. So this is showing some comparisons of how the air vent open positions are along with the results from the simulation. So all of this is also available as a reference in a PhD thesis. Chute design, of course, is another one of the areas where DEM is commonly used, especially to prevent plugging at impact points. So being able to include body motion then allows us to precisely define the timeline and characteristics of how this process will begins. And all the elements of particle flow, abrasion, and the motion of the internals can be captured in STAR-CCM+. But the key point here is that one simulation will probably give you an insight into the behavior, but not necessarily solve the problem. So if there is a design goal, one need to investigate several different designs. And the question is that, how do I do this? Do I do this one simulation at a time? Or is there a better way of looking at or exploring this design space or operating condition space, if you will? And at that point, we are going to come towards the end of the talk. Here is another example, which is coming from pharmaceutical company, Takeda. So again, here, segregation of particles based on sizes of particles was a critical issue. And one of these particles is a drug substance. So if you have segregation of the drug substance from the excipient, the regulator requires you to bump up the dosage of this drug substance in order to cover for those losses. This would mean that then the pharmaceutical company has to spend a lot more money in this expensive drug substance in order to cover for that shortfall. So they were trying to look for a design that will minimize this segregation. So with the help of simulation, they found which design would be the best one. And on a lab scale, investigated by doing that experiments with 3D printing. And it is estimated that it had an impact of several hundreds of thousands of dollars in terms of scaling up this process from the lab scale to the production scale, as well as reducing the time that would have been required to scale up if everything was done kind of purely experimentally. Now we come to the part where we know that particles sort of do not exist in vacuum. They are always accompanied by fluid. Sometimes the interaction is very tight and there is two-way interactions. Other times there is one-way interaction. So STAR-CCM+ allows you to capture these interactions very easily. We start by looking at what happens if you have a air injection into a bed of particles. So we see this type of situation quite commonly in blast furnaces and other steel operations. So we start to see, as we increase the velocity, in this example from 7 to 10 meters per second, it starts to form a small bubble here, and then the air that is injected start to escape out. As you start to increase the velocity of the air, this region grows until it reaches a point where there is a small cavity that is created. And the top pictures are actually showing you photographs from this experimental investigation. Just bear in mind that these two are at different scales. So although this cavity looks large here, it is similar in shape here. And just from the scale perspective, this is much more zoomed in images that we get from the simulation. So by doing this investigation, one of our users was able to really apply this to their industrial case problem and solve this quite successfully in understanding what kind of cavity would be created. We have done similar type of exercises, also spouted bed, which is, let's say we can call it a type of fluidized bed activity. Here we can see the power spectral density and its response with respect to frequency. We all know that DM simulation can be expensive, so we use a method called as coarse graining, which means that you create numerical particles, and in each numerical particle constitutes several real particles. So in the end, that with the help of coarse grain, we can reduce the computational effort, but can still reproduce the sort of dynamic response of this bed that we see from the experiment as well. Again, this is replicating some of the work that has been published in literature as well. So we do this type of exercise of validating the physics quite often in order to make sure that the results that we get from simulation are in line with the reality. One of the key outputs that we have seen, PSRI, which is the Particle Solid Research Institute based out of Chicago, investigate is that how do particles collide with each other when they are fluidized. And so they do an experiment called as a jet cup experiment, where you add particles and a fluid jet, and then they rotate around here in the cup. And for longest time, it was a hypothesis that the particle wall collisions were the primary responsible physics that was causing attrition of these particles, especially these type of things where we see are used in catalytic fluidized bed. But with the help of discrete element modeling and looking at the frequencies of particle-particle and particle wall collisions, which otherwise is almost impossible to see into this phenomena, we found out that the particle-particle collisions occur at much higher frequency and also at much higher severity. And so this was a key step in creating further mechanistic models to understand how particle attrition occurs in jets, commonly seen in the refining industry. Of course, it's not just refining and steel industry where particle flows are common. We see those also in the pharmaceutical industry, and some of the processes such as granulation and drying are very, very common. Here is another example of a fluidized bed granulator, where you have fluidizing air, which is causing the particles to be fluidized in this region, the upper region, as well as the lower region. And then there is a spray here that is creating liquid droplets in the spray zone. And these droplets essentially coat the particles, and these particles then circulate within the granulator several times before they are coated to a certain degree that is desired. So all the rest of the parameters in terms of the properties, they are kind of listed in this table here. So STAR-CCM Plus actually allows you to look at not only the air that is flowing and causing the fluidization of the particles, but also the spray, which is liquid droplets. And then we use sort of a counter to calculate how much of the droplets from the spray will get coated onto the particles. And then we use the counter because these particles are passing through the spray zone several times until we can come to a conclusion what is the coating thickness that is achieved. And so in this study, which was done at the Center for Structured Organic Particles, an investigation was done in terms of if there is a changing rate of air supplied, it causes different levels of fluidization, which then affects the collision frequencies. Therefore, it affects the passage frequency of the particles, and it has an effect on how much of coating that you would get on these particles. So eventually, the average collision frequency in the top compartment versus the bottom compartment could be compared, and we see that the collisions in the top compartment are significantly lower in comparison to what is seen in the bottom compartment. This then calls for possibly an adjustment in the design, either of the spray itself or maybe the location, so that the overall residence time of the particles can be optimized in order to achieve the level of coating that is required. So the number of particles that are passing through over the total number of particles essentially tells me how the residence time distribution of these particles is going to be in the spray zone. And this is sort of the critical process parameter that defines the efficiency of the whole granulation process itself. Here is another example where not only the particle transport and the physical behavior of particles breaking or aggregating was investigated, but it was combined with what is called as population balance methodology. That means we look at the population of particles at a certain size and how does that change because of addition of these binder droplets that cause the particles to agglomerate when they see the binder, or break whenever there is high amount of shear. So we can capture the key sensitivities of the critical product attributes and link them to the design of the equipment itself. And this is a key step in achieving what is called as the quality by design initiative, which is the buzzword in the pharmaceutical ingredient manufacturing. So on one hand side, we have the characteristics that we get from discrete element modeling. And on the other hand side, we have a population balance model that is looking at the agglomeration and breakage rate. And then we interface them and exchange the information between the two sides. So what we see in this animation is essentially the diameter of the particle, the porosity, and the liquid fraction of the droplets that are added with respect to time as they are progressing. And because of that, the agglomeration of the particles that is caused changes the size distribution of the particles themselves. And if you look very closely, or if the animation is coming out through the internet very well, you can see in general there are more number of larger particles as the time progresses, and shows you the shift of the distribution itself. So the impact is that the effect of these geometries, that means the shape of the screw, the addition of the liquids, the rate of transport, and the number of screw elements that we have, we can investigate them in a virtual environment to see what is the impact on the product quality. So effect of RPM on various particle parameters can be captured, and then in conjunction with the population balance model can be investigated to look at the changes in the particle size distribution itself. Adam, how are we doing on time? Do I have maybe another 5 minutes or so that I could speak?
Rather, yes, you have as long as you need. So keep going if you want to dive into more detail.
Okay, maybe last couple of examples. So this is a fluidized bed dryer example, and this is really a key insight into how various physics within STAR-CCM Plus can be utilized with each other. So you have moist particles that are coming in, and there is dry air that is introduced, and the goal is that the moisture from the particles will get transferred to the air. So not only we need to capture, how these particles are fluidized, but we also need to include the evaporation of the water from the particles into the dry air that is flowing through. So we can define the rate of water evaporation of the particles, based on typical mass balance relationships that we see, which includes the vapor pressure of the water that is evaporating inside the particle as well as in the dry air. And then we can connect them in a very simplistic manner, including the field function capabilities in STAR-CCM Plus. And in this, then we can define, what is the activity coefficient of water based on the moisture content. That means it defines basically how much of the water from the particle will be transferred into the air phase. And then we define the coefficients that are correlating that transfer coefficients from the solid side, that is the particle side, to the liquid side. And then they are connected with the diffusivity as well as the heat transfer that happens from the dry air, the dry hot air to the cold moist particles, if you will. And then as a result, what we see is essentially over physical time, how is the moisture content of the particle on an average basis is changing. Here on the figure on the left, you can see the mass fraction of water that is plotted in the gas phase, which is the colored phase here. And then the moisture content of the particles themselves, which is plotted on the grayscale. Now I can see that due to the color contrast here, it is a little bit difficult to discern the differences. But essentially what we see is the particles at the bottom have much higher moisture content, and as they fluidize and start to exit the dryer, they become less and less in terms of the intensity in the dark gray color here, losing the moisture to the air that is flowing through. Let me end with an example of coating, and especially talking about how simulation is to be used in the context of solving engineering problems. So coating is another very key unit operation in the pharmaceutical industry. You have a spray. I gave you a previous example, which was fluidized bed. In this case, this is a rotary coater. And we have these two coaters, which are showing you an example of a single spray versus two sprays. We can, of course, also investigate what is the effect of the baffle design and so forth. So if you go from a single spray to a two spray design, I can see that the standard deviation reduces from this green curve here to the red curve, which just tells me that two sprays are more effective in reducing the non-uniformity of the coating thickness in the particles, which is an obvious conclusion. But the key question then we have to ask is, how can I utilize this in order to find a design or find a operating condition that will give me the most optimum design or most optimum condition that reduces my deviation of the coating uniformity. And this is essentially what we tried to do this in an example. So of course, here we are utilizing that we can capture the tablet shapes of particles as well. So cut cylinders, if you will. Here we use which in principle is a third phase, which is for the spray that is hitting the particles. And now we want to automatically and intelligently search for the design that gives me the best coating uniformity. So design space exploration is a concept which tries to address multiple challenges in a single study. So we want to maximize efficiency, we want to maximize distributions, minimize perhaps energy consumption, avoid excessive wear and abrasion in designs, and optimize overall performance at the whole system level. And when we start to see many of these words, maximize, minimize, that are occurring together, we immediately see that this is not a single simulation problem, but it needs multiple simulations that need to be repeated in order to balance the various objectives, right? There are always counteractive acting parameters, and possible multiple designs and experiments might be necessary in order to find the solution. So typical simulations say that if you spend certain amount of time building the model, then very little time is left in order to explore many different designs and to really assess what the engineering simulation is going to be. Our approach has always been that we can see that the most value comes if we can investigate many different possibilities and from them find what the optimum is. And therefore, we need to assign our engineering time in line with that value. So we need to create the model once, thereby reducing the time that is required to build. And then we need to reuse it several times for a given problem statement that has such a complexity shown on the left side, in order to have the utilization of time in line with where we see the value, which is explore and assess the results. And that's the way we can discover better designs. So we want to move from the typical usage cases where we use simulation to validate something or troubleshoot something, maybe also to the extent of predict, but really move higher up the scale where we can automate this process and really explore those designs. So we applied the same thing to this coating simulation. So here we can look at the number of tablets that are coated as well as damaged, and calculate some sort of a damage index, which is expressed as a formula below here. So this is the baseline case. Here we have a certain design of baffles, which are 50 millimeters in height, and a certain twist angle, and there are 4 of these baffles here. And the question we ask is, can I find a certain configuration of baffles within these design configurations, which will maximize my coating uniformity and at the same time minimize the damage that is caused to the tablets. And so what we get is a process where we build the model first, which includes the mesh and everything else. And then we test the baseline model, do the analysis. And then we start to repeat this process automatically so that finally we can assess the results from all of these investigations altogether. And this is, you can call it, virtual prototyping, if you will. So in this process, we can specify what are the different variants we want. We can specify the minimum and the maximum limits to those design variables. We can define what are the increments that we need to do them. We can also include any exceptions that we want to include in the study as well. So in the study, we investigated about 125 different possible configurations. And this is not a brute force approach, mind you. Since we define the goal, that means I want to minimize certain thing and maximize something else. We've tried to find that we get to the goal with minimum possible investigations. Right? So took about 2 hours, simulate 13 seconds on 4 cores, and then it is repeated about 125 times, spawning on a set of cluster nodes. And what we see is, as these designs are explored, what is the increase in the coating rate in terms of the coated tablet count that we get in order to maximize the coating rate. And finally, we arrive at a final design. So this best design reduces the damage index by about 2%, while it is increasing the coating uniformity. And here we see the smallest damage index. So going from baseline design to this particular design number 15 through that iterative process. I'm sorry, something is missing here. We reduce the damage index by several tens of % and increase the coating uniformity by about 30% or so. So that is kind of a parting message, if you will, that I want to leave with, that exploring the entire operating space is a key component in order to investigate and arrive at an optimum operating condition or a design of a given equipment. And we use intelligent search algorithms, but all of that is only possible if we have the right type of physics, which is coupling not only the particle flows, but also the fluid flow and the associated physics with it together. So I will stop there, Adam, and
Excellent.
see if there are questions and comments from anyone.
That was really good. Thank you, Ravi, for going into that and the detail there. Jonathan, do you think you could unmute everyone? And if anyone has any questions at this point, let's hear them. Either speak them, or if you'd rather put them into the chat, whichever you prefer.
Yep, absolutely. So everyone should now be able to unmute yourself. If you just kind of hover over this shared window, bottom left is the mute unmute button. You can also ask chat questions. Those will come directly to us, and I can moderate those in. One question I had up front, and Adam, this might be more of a question for you, is what does it take to license this stuff? Like, is this an add-on that we need on top of our regular STAR licenses, or what does that look like?
Yes, and so the DEM piece of STAR-CCM Plus is included with every license. So it's not a barrier to try it out. Anyone who's got STAR can try it, and there's really no cost above the regular licensing to use DEM. So, and the same with the FE solver too. All of the things that Ravi's talked about are included in the base license. So that makes it very easy to use any of these technologies when you need to. All right, thank you, Jonathan, for that question.
Yeah, absolutely. Waiting for any other questions to come in. Feel free to put those in now. Adam and Ravi, can you guys just speak a little more to the compatibility of the DEM solver with the other physics solvers?
Yes. So, primarily the DEM solver and the CFD solver, they share the same variable space, if you will. That means any variable that is in the CFD solver is accessible to the DEM solver, and that's why it becomes quite easy to write any sort of expressions connecting them. So the example that I gave about the fluidized bed dryer essentially tries to do that. It connects the moisture content on the fluid side with the moisture content on the DEM side, because I have this possibility that I can write an expression that says, that much amount of moisture from the particle will be evaporated and then transferred into the fluid phase. So most of the physics that is available in the CFD solver is kind of out of the box compatible with the DEM part.
Is it recommended to use the double precision or mixed precision solvers with the DEM?
It depends on problem to problem. We generally provide a best practice guideline, depending on what is the physics involved. So there is no clear answer. I think the best practice guideline essentially is the path to understand which solver to use.
Ravi, this is Adam. Can you comment a little bit on HPC compatibility and scalability?
Yes. So the DEM solver is completely parallelized, just like the CFD solver, and it is also dynamically parallelized in the sense that if in a given problem you have more particles in one area of the domain versus the other area of the domain, then automatically the code will assign more cores to where there are large number of particles versus there are lower number of particles. You can parallelize it to high core counts, and it's basically defined on what is the limit of the final number of particles you can have per core before it starts to lose its speed up advantage, and that goes down all the way up to almost 1,000 particles. So if you had 1,000,000 particles, you could run it on 1,000 cores, each core having 1,000 particles, and still get a linear type of scale up there.
Excellent. Okay. Well, it looks like we've got no other questions. If anyone's got any, if they could shout now, that would be good. Otherwise, we appreciate your time, and we'll wrap up the meeting. Thank you, everybody.
Sounds excellent. Thank you all.
Thank you, Ravi. Have a good
Thank you.
afternoon.